Let us discuss nitrogen family in the P block elements. In the nitrogen family, what are the elements are present? We'll see. Nitrogen family contains nitrogen, phosphorus, arsenic, antimony, and bismuth. Nitrogen family contains these are the elements. Okay. What is the occurrence of these elements? These elements are available from where? That we'll see. Occurrence we'll see. Nitrogen is available in the atmospheric air, we know. Then nitrogen salts we will see. Nitrogen is available in the form of salts. The salt is called calichy. Another name is called chili salt peter. Chili salt peter. The chili salt peter formula is NaNO3. NaNO3. Next, Indian saltpeter, that is KNO3. Indian saltpeter, we can say. Indian saltpeter is what in the sense KNO3 we can say. These are the occurrence of nitrogen. Then phosphorus we will see. Phosphorus is available in the form of salt. That salt is called apatite we can say. That salt is apatite. The apatite general formula is Ca9 PO4 6 times CaX2. In the place of X, what we can take? In the place of X, we can take FClOH. We can take like this. So, for this apatite, what is the example? Example will say, in the place of X, if you write F, then this apatite becomes a fluorapatite. 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 This formula is Ca9 PO4 6 times. In the place of X, we will write F. In the place of X, we are writing F, we are writing. Okay. So phosphorus is existing in the form of, is available in the form of apatite. Example is fluorapatite, we are saying. Fluorapatite in the sense, in the place of X, we are substituting F. Next, we'll take arsenic, antimony, and bismuth. These are available in the form of sulfides. Arsenic, antimony, and bismuth. These are available in the form of sulfide minerals. Arsenic sulfide, antimony sulfide, bismuth sulfide, like this available. Then these family elements that metallic and non-metallic nature we will discuss. Nitrogen and phosphorus coming under non-metals. Nitrogen and phosphorus coming under non-metals. Arsenic and antimony metalloids. Arsenic and antimony metalloids. Metalloids in the sense metallic nature as well as non-metallic nature. Then bismuth is a typical metal. Bismuth comes under metal, we are saying. Sir. Next, we'll see that element molecular formula we'll see. In the elemental nature, what is the molecular formula of these compounds? We'll see nitrogen element if we take, that consists of N2 molecules. Phosphorus element if we take, that consists of P4 molecules. Like this, arsenic if you see, AsS4 molecules. Arsenic exists as AsS4 molecules. Antimony Sb4 molecules, bismuth Bi4 molecules. Okay. Now, in this elemental nature, if you see, nitrogen exists as a diatomic. Nitrogen exists as a diatomic. Rest exists as a tetraatomic in this group, in this family. So, nitrogen is showing diatomic nature. Rest of the elements showing tetraatomic nature. What is the reason? That we will see. Now, nitrogen will take and phosphorus will take. Nitrogen size is what in the sense low. Phosphorus size is high. Size of the atom. Nitrogen size is low, phosphorus size is high. Therefore, size is low in the sense distance between nucleus and outer orbital is low. Here distance is high. Therefore, in this place, lateral overlapping means pi bonding. Lateral overlapping takes place to high extent, but here lateral overlapping takes place to low extent. Lateral overlapping means pi bonding. Okay. Here distance between nucleus and valency orbital is less. Therefore, lateral overlapping takes place higher extent, but here lateral overlapping takes place lower extent. Therefore, in this place, pi bond formation tendency is high. Pi bond formation tendency is high. but pi bond formation tendency is low. Therefore, here pi bonding easily forming, pi bonding is not easily forming. Therefore, it is existing as a nitrogen molecule N triple bond N. In this one sigma bond and two pi bonds are there. But in this case, P triple bond P is not possible. P triple bond P is not possible because lateral overlapping tendency is low here, pi bonding tendency is low here. Therefore, this phosphorus is not existing as P2, is not existing as like this. Then phosphorus existing as what? Phosphorus existing as like this. Now we will take four phosphorus atoms. We will take four phosphorus atoms. We will keep at the corners of tetrahedron. At the corners of tetrahedron, you keep four phosphorus atoms. Tetrahedron center point you leave as vacant here. Then between phosphorus atoms, a single bond is possible. Between phosphorus atoms, single bond is possible. Now, each phosphorus atom is making three normal covalent bonds here. Now, phosphorus is having lone pair. Each phosphorus is having one lone pair. Why? Because phosphorus coming under fifth year group, its valence shell contains 5 electrons. Out of 5 electrons, 3 electrons have gone for bonding. Remaining 2 electrons remaining as a lone pair for this phosphorus. Okay, so phosphorus is existing as P4 like this. Phosphorus, arsenic like this. Therefore, in the elemental form, in this nitrogen family, phosphorus, arsenic, antimony, bismuth exist as tetraatomic, while nitrogen exists as a diatomic. Why? Because nitrogen size is low, lateral overlapping is possible here to higher extent. Therefore, pi bond tendency is higher extent here. Therefore, nitrogen exists as a diatomic, but phosphorus size is high, lateral overlapping tendency is low, pi bonding tendency is low. Therefore, like this, P2 is not possible. Like this only possible. Phosphorus existing like this. Therefore, by this point, can we say that phosphorus never forms pi bond? That is wrong. Phosphorus also can form pi bond. Phosphorus is forming pi bond with oxygen. Phosphorus is forming pi bond, but in elemental form, phosphorus is not existing as P2. In elemental form, phosphorus is not existing as P2, it is existing as P4. In the elemental form, nitrogen existing as N2, not as N4. Okay, in elemental form, we are talking, not for other molecules. Phosphorus is forming many molecules. In the many molecules, phosphorus is having multiple bonds. Phosphorus is making double bond with oxygen. In elemental form, we have spoke. Okay, so we have spoken in the elemental form, phosphorus existing in tetraatomic while nitrogen existing in diatomic. It is experiment. For this experiment, we have given a explanation like this. It is not indicating that phosphorus never forms pi bond. Okay, sir. Phosphorus also forms pi bond with oxygen. Many molecules are there in which between phosphorus and oxygen double bond is there. In the double bond, one bond is pi bond. Sir. So we have discussed elemental form alone. We have discussed here. Elemental form alone we have discussed. As per that we said. Sir. Then this nitrogen is a diatomic. Rest of the elements are a tetraatomic. We said elemental form. Then we will see physical state. We will see physical state of nitrogen is gas. Rest of the elements solid. Rest of the elements solid. Physical state of nitrogen is gas. We are saying rest of the elements we are saying solid. Why is it so? That means phosphorus, arsenic, antimony, and bismuth existing as solid, but nitrogen exists as gas. What is the reason? That means now we will take nitrogen molecule and rest of the molecules we will take. Now we will take nitrogen molecule and phosphorus molecule. Nitrogen molecule we can say like this. Phosphorus molecule we are saying like this. Phosphorus molecule we are saying like this. Now we will see size of nitrogen molecule. Size of nitrogen molecule is low. Size of phosphorus molecule is high. Now see, nitrogen molecule contains nitrogen atoms. Here dipole moment is not there. This bond is not having dipole moment because bonded atoms are having same electronegativity. Dipole moment is not there. Therefore, it is non-polar molecule. Non-polar molecule means only one type of intermolecular force of attraction is possible, that is instantaneous dipole. Induced instantaneous dipole attraction only possible, which comes under van der Waals force of attraction. Okay, so non-polar molecules means only one type of intermolecular force. What is that? Instantaneous dipole, induced instantaneous dipole. That only possible. Okay, so it is non-polar molecule, therefore instantaneous dipole, induced instantaneous dipole, that is called van der Waals force possible. Van der Waals force depends on size of the molecule. Size of the molecule is low means van der Waals force also low. So here size of molecule is high, therefore van der Waals force is high. So here between nitrogen molecules, van der Waals force is low, therefore intermolecular force of attraction between nitrogen molecules is low, therefore nitrogen existing as gas. Phosphorus molecules, between phosphorus molecules, van der Waals force magnitude is high, therefore intermolecular force of attraction between molecules is high, therefore phosphorus molecule existing as solid at room temperature. So at room temperature, nitrogen is existing as gas, whereas the rest of the elements in the nitrogen family existing as solid. Because of this reason, we can say. So next we will see in the nitrogen family, we will see the catenation. We'll see catenation. What is catenation? Similar elements linked with each other, that is called catenation. Now nitrogen we are taking. Nitrogen if we take, it is showing catenation. In the catenation, in the sense, similar elements linked with each other like this. If you see, it is hydrazine. This is called hydrazine. Like this phosphorus, if you see, diphosphine. So similar elements linked with each other. This is called catenation. Similar elements linked with each other, that is called catenation. We can say catenation depends on bond energy. Okay, so bond energy of Nn, bond energy of Pp will see. So bond energy of Nn, bond energy of Pp, if we see, which is having higher bond energy, do you think? Bond energy is high, bond energy is low, because smaller atoms, nitrogen is smaller size, phosphorus is higher size. Smaller atoms means here overlapping tendency is more, bond strength is more, bond energy is more. Phosphorus atoms larger size, so overlapping tendency is low, therefore bond strength is low, the bond energy is low. Therefore bond energy is high means catenation power will be high, bond energy is low means catenation power will be low. Therefore down the group, how the catenation power will be there, that we'll see. We'll write nitrogen, phosphorus, arsenic, antimony, bismuth. We will say in the from phosphorus to bismuth, what happens to the size? Means size increases, therefore bond energy decreases, therefore catenation power what happens means decreases. So nitrogen to phosphorus, we'll see. Nitrogen to phosphorus, what happens to the catenation power? In the sense, the catenation power increases. That means not only bond energy, some other factor also playing a role. That's why catenation is like this. So nitrogen and phosphorus catenation, if you see, catenation power is high for phosphorus, nitrogen is low. Why? Because in the nitrogen, lone pair repulsion is there. Due to lone pair repulsion, the catenation power of this nitrogen is low when compared to phosphorus. So in the nitrogen family, which is having highest catenation power, in the sense phosphorus is having highest catenation power. Catenation power of nitrogen is lesser than that of phosphorus, because lone pair repulsion is dominant in the nitrogen. That's why like this happening. So next we'll see oxidation states. We'll see what is the oxidation states of these elements, that we'll see. Now we are going for oxidation states. Oxidation states will take a nitrogen family, will take nitrogen, phosphorus, arsenic, antimony, bismuth. We are taking its valence shell. Its valence shell electronic configuration is what means ns2 np3. Its valence shell electronic configuration is ns2 np3. The valence shell is having 5 electrons, so it is in need of 3 electrons to get octet. If they gain 3 electrons, then they form a 3 minus oxidation number, N3 minus we can call it as a nitride we can call. Then P3 minus we can call it as a phosphide. P3 minus we are calling as phosphide. AS3 minus we can call it as a arsenide. AS3 minus arsenide. Sb3 minus we can call it as a antimonide. Antimonide we can say. Then Bi3 minus we can call it as a bismuthide. Bi3 minus we can call it as a bismuthide. Okay, so these 5A group elements can show oxidation number -3. -3 oxidation state they are showing. This -3 oxidation state down the group stability, how it will be there? Stability of -3 state. Down the group stability of -3 state decreases because electronegativity of these elements decreases down the group. Okay, so -3 stability, what happens to these elements? Down the group, -3 stability decreases because electronegativity decreases, we are saying. Okay, so next we will see. Next, this ns2 np3 we are writing like this. ns2 np3 we are writing like this. Here 2 electrons, here 3 electrons. If these 3 electrons alone involve in chemical reaction, if these 3 electrons alone involve in chemical reaction, then these elements can show +3 oxidation state. These elements can show +3 oxidation state. So now we will take nitrogen, phosphorus, arsenic, antimony and bismuth. Now down the group, what happens to the stability of +3? Down the group stability of +3 increases, we can say. Down the group +3 stability, what happens? Increases. And if these 5 electrons involve in chemical reaction, these 5 electrons involve in chemical reaction in the sense they can show +5 oxidation state. +5 oxidation state. Down the group, what happens to the stability of +5 oxidation state in the sense that is decreasing. Down the group, +5 oxidation state decreases. +3 stability increases. Why is it so? That we will see. Now we will take bismuth. Bismuth electronic configuration is what means xenon, 4f14, 5d10, 6s2, 6p3, 6d0. It is the electronic configuration of bismuth. Now, what is the valence shell? Valence shell is a 6s2, 6s2, 6p3. 6s2, 6p3 we can say. It is ground state. Now, excited state we will see. Excited state in the sense from 6s, one electron goes to 6d. From 6s, one electron goes to 6d. Now, if we see number of unpaired electrons, 5. If these 5 unpaired electrons involve in chemical reaction, then this element can show +5 oxidation state. If here in ground state 3 unpaired electrons are there, if these 3 unpaired electrons involve in chemical reaction, then the bismuth will show +3 oxidation state. Now this ground state and excited state we will compare. Now this 4f14 shows very poor screening effect. 5d also shows poor screening effect. Screening effect order, if you see, S is greater than P, P is greater than D, D is greater than F. So this F shows very poor screening effect. Due to very poor screening effect, attraction between bismuth nucleus and 6s electrons is high. Due to higher attraction, the 6s electrons unable to go for unpairing. The 6s electrons is difficult to go for unpairing. It's difficult to go for unpairing. Therefore, +5 stability is low for bismuth and +3 stability is high for bismuth. So that for bismuth case, how the +3 stability and +5 stability is there in the sense +3 stability is high and +5 stability is low for bismuth. This effect is called inert pair effect because the 6s electrons is unable to, it is 6s electrons is difficult to go for unpairing, is difficult to go for chemical reaction. Therefore 6s electrons is like inert, therefore it is pair of electrons. Therefore this effect is called inert pair effect. Due to inert pair effect, +3 stability of bismuth is high when compared to +5 stability. So for bismuth, we can say +3 stability is higher than +5 stability due to inner pair effect. That inner pair effect is due to very poor screening effect shown by 4f14. Sir, down the group, how it will be there, that we will see. Now we will see nitrogen. Nitrogen electronic configuration is helium 2s2 2p3. Then phosphorus will take in the nitrogen. If we see, the valence shell contains 2s and 2p. The valence shell is not containing any more orbitals. Therefore, these 2s electrons do not go for unpairing. Okay. Therefore, nitrogen can show maximum covalency. How much means 4. Nitrogen can form 3 normal covalent bonds and 1 dative bond. This electron pair will be contributed for dative bonding. So nitrogen can form maximum covalency 4. Nitrogen can form maximum covalency 4. 3 normal covalent bonds and 1 dative bond. That's all. Phosphorus, if we see electronic configuration neon 3s2 3p3, 3s2 3p3, 3d0 is there. So phosphorus, if we see, 3s contains 2 electrons, 3p contains 3 electrons, 3d contains vacant. Okay, it is ground state. Excited state, if we see, this from 3s 1 electron goes to 3d, 1 electron goes to 3d. So 5 unpaired electrons are there. Now in the phosphorus excited state, 5 unpaired electrons are there. Okay. Next, arsenic is what in the sense argon 3d10 4s2 4p3. So this 3d10 shows poor screening effect. Therefore 4s electrons is somewhat difficult to go for unpairing. Antimony, krypton 4d10 5s2 5p3. So because of 4d10 poor screening effect, this 5s electrons is getting somewhat difficult to go for unpairing. Therefore, down the group, what happens to the inert pair effect? Down the group, inert pair effect tendency increases. Down the group, inert pair effect tendency increases. Therefore, stability of +5 decreases and stability of +3 increases down the group, we can say. So now what is the common oxidation states of this group in the nitrogen family? In this nitrogen family, what is the common oxidation states in the sense one is -3, next one is +3 and another one is +5. In addition, some other oxidation states also possible. Common oxidation states means -3 +3 +5. Why -3? Because it is group number 5a. If it takes 3 electrons, it will get octet. Therefore, -3. Why +3? In the ground state, 3 unpaired electrons are there. If 3 unpaired electrons involve in chemical reaction, then +3. Why +5? In excited state, 5 unpaired electrons are there. If 5 electrons involve in chemical reaction, then +5. Sir, why do we say unpaired electrons? Okay. Why do we say unpaired electrons? That we will see. Now we will take what in the sense PCl3 will take. PCl3 in the sense, now see that PCl3 we are writing like this. PCl5 will take. PCl5 we are writing like this. So phosphorus is making 5 single bonds. Therefore, here phosphorus provided 5 unpaired electrons. Here phosphorus made 3 single bonds. Phosphorus provided 3 unpaired electrons. So here phosphorus is providing 3 unpaired electrons for forming 3 bonds. Phosphorus is providing 5 unpaired electrons for forming 5 bonds. Now Cl can show -1 oxidation state. Therefore phosphorus can show +5. Cl can show -1. So phosphorus can show +3. Okay, sir. We explained like this. What about nitrogen case? Nitrogen is having 3 single bonds. Nitrogen is having 3 unpaired electrons. Nitrogen cannot show. Nitrogen cannot give 5 unpaired electrons. Nitrogen cannot give 5 unpaired electrons because in its valence shell no more orbitals present. In the valence shell of nitrogen, no more orbitals present. Therefore, nitrogen cannot give 5 unpaired electrons. Therefore, that means can't nitrogen show +5 oxidation state? Of course, nitrogen can show +5 oxidation state. Nitrogen can show +5 oxidation state, but nitrogen cannot form 5 bonds. Nitrogen cannot form 5 bonds because 5 unpaired electrons not there in nitrogen. So in the nitrogen, 5 unpaired electrons is not there. Therefore, nitrogen cannot form 5 bonds. Nitrogen can form maximum 4 bonds. In the 4 bonds, 3 are normal covalent bonds. One is a dative bond. So nitrogen is having 3 unpaired electrons. So it is forming 3 normal covalent bonds. It is having electron pair. This nitrogen can contribute to electron pair for dative bonding. So nitrogen can show maximum covalency 4. In that 4, 3 are normal covalent bonds. One is dative bonding. Rest of the elements can show 5 covalency normally. Not only 5, more than 5 also can show. How phosphorus can show more than 5, that we'll see. Now we have taken PCl5. Now another PCl5 will take. Now another PCl5 we have taken. Now what happens? You see that this Cl is having 3 lone pairs. Now this phosphorus is having vacant orbital. The Cl is contributing electron pair to this vacant orbital phosphorus. Therefore, this bond is shifting towards Cl. So this is becoming what you see, PCl4. PCl4. It is becoming what in the sense? PCl6. It is becoming PCl6. Now this phosphorus is losing the bond. Therefore, phosphorus is getting positive charge. This phosphorus is gaining the bond. Therefore, getting negative charge. This Cl is making a bond this side, gaining the bond this side. So no change for this Cl. So no charge. So that now you see that phosphorus is making how many bonds here? 6 bonds it is forming. Okay, so nitrogen means 3 normal covalent bonds, general. Otherwise, additional 1 dative bond. So nitrogen can show maximum covalency how much? 4. Rest of the elements can show 5 covalency, no doubt. More than 5 also it will show. Phosphorus can show 6 also. Okay, so how the covalency of these elements are there, that we have seen. Next, we will see what are the rest of the oxidation states. They will show general oxidation state. We said -3 plus 3 plus 5. What is the other variable oxidation numbers, that we will see. Nitrogen, if you see, nitrogen if we take, it will show oxidation state from -3 to +5. Okay, so -3 possible in ammonia, -2 possible in NH4, -1 possible, -1 is possible in then 0 oxidation state possible in N2, +1 possible in N2O, +2 possible in NO, +3 possible in N2O3, +4 possible in NO2, +5 possibility in N2O5. So nitrogen can show variable oxidation states. Even nitrogen can show -1/3 in N3, N3 minus. In N3 minus, nitrogen can show -1/3 oxidation state. So nitrogen, if we take a variable oxidation states, it shows now we will take NH2OH. We will take in NH2OH nitrogen oxidation state. We will find nitrogen, 3 hydrogens are there, therefore +3. Okay, then oxygen -2 will take, equal to 0 will take. So nitrogen oxidation number, if you see, -1. So nitrogen can show -1 in NH2OH hydroxylamine. So nitrogen can show variable oxidation states from -3 to +5. Okay, sir. Now we have said about oxidation states. Next we will see about disproportionation, that we'll see. We'll see about disproportionation, we'll see. Okay, sir. What is a disproportionation? That point we'll see. Now we will take. We will take HNO2. In HNO2, nitrogen shows oxidation state +3. Nitrogen can show maximum oxidation state +5. Minimum oxidation state how much in the sense? -3. Sir. Now, this nitrous acid, we are using for diazodization reaction. Nitrous acid we are using for diazodization reaction. The nitrous acid, we said in the diazodization reaction, we have to keep temperature 0 to 5 degrees Celsius. Why? Because 0 to 5 degrees Celsius, because diazonium salt is unstable. Therefore, we have to keep 0 to 5 degrees Celsius. And for diazodization, we want nitrous acid. We are preparing nitrous acid in situ because nitrous acid is unstable. Why? Because nitrous acid undergoes disproportionation easily. That means this +3 is undergoing oxidation and becomes +5. Then this +3 undergoing reduction and becomes a +2. So nitrogen is undergoing oxidation to +5 and another nitrogen is undergoing reduction to +2. That means this nitrogen itself undergoes oxidation as well as reduction. Therefore, nitrous acid can undergo disproportionation. Therefore, nitrous acid is unstable. Therefore, whenever we need nitrous acid, we have to prepare in situ. In situ means at that time we have to prepare, immediately we have to use it. In situ means that will be produced in the during the chemical reaction. At that time, at the spot, we have to prepare and we have to use it. Therefore, nitrous acid we are preparing at that time itself. At that time we are preparing and we are using. We are not preparing and we are not storing. Okay. So because nitrous acid is unstable, it can undergo disproportionation. So nitrogen +3 is undergoing oxidation to +5 in one side and +2 reduction in another side. Let us balance this one. Now we will make loss and gain of electrons equal. This +3 is converting into +5 in the sense loss is equal to 2 electrons. +3 is converting into +2 in the sense gain is equal to 1 electron. Let us make loss and gain equal. So loss is 2, make gain also 2. Therefore, multiply this with 2. Okay, so 2 nitrogens converting like this, 1 nitrogen converting like this, totally 3 nitrogens. Therefore, keep 3. Okay, so 3 HNO2 gives HNO3 and the NO we are saying. Let us balance the rest of the things. Now we will balance oxygen is balanced or not. You see here oxygen is 6 present, here 3, here 2, 5. Remaining one oxygen is there. For that you write water molecule. Now let us balance hydrogen. Here 2, here 1, 3, here also 3. Hydrogen is balanced. Here nitrous acid can undergo disproportionation, we said. Then let us take NO2. Let us pass NO2 in water. What will happen? Okay, so we are passing NO2 into water. What is happening? That we will see here. NO2 in that nitrogen oxidation number is +4. Nitrogen can show maximum how much oxidation number? +5. So NO2 is converting into what in the sense NO2 nitrogen +4 is converting into +5. Then this +4 is converting into +5 in the sense this is called oxidation, we can say. That is oxidation we are saying. Okay, here what is the loss of electrons? What is a loss of electrons in the sense 1 electron is lost. Then +4 is converting into +2. Here reduction possible. Here gain of electrons how much means 2 electrons gain. Make loss and gain equal. For that case multiply this with 2. Then loss and gain will be equal. Okay, so now we have to take how many nitrogen means 3 nitrogen we have to take. Okay, then let us balance oxygen. Here 6 oxygens present. Here 6 plus 1 7. For this oxygen we are writing water molecule. Now we will balance hydrogen. Hydrogen is 2, hydrogen is 2. This is disproportionation reaction we are seeing. Okay, so nitrogen +3 is undergoing disproportionation. +3 is converting into +5 and +3 is converting into +2. Then NO2. In NO2, nitrogen is +4. It is undergoing oxidation and become +5 and undergoing reduction and becomes +2. Okay, disproportionation reaction we said. Next disproportionation we will see. Now we will take H3PO3 we will take. In H3PO3, phosphorus is +3. It is undergoing oxidation. Oxidation means +3 is converting into +5. +3 is converting into +5. Phosphorus cannot show +4. +3 is converting into +5. Oxidation. Then reduction will see this +3 is converting into what in the sense least oxidation number, that is -3. Least oxidation number +3 is converting into -3. Here gain of how many electrons in the sense 6 electrons gained. Here +3 is converting into +5. Loss how much in the sense 2 electrons. Let us make loss and gain equal. So for that case, what shall we do in the sense we will make this is as 1, we will make this is as 3, okay, because divide by 2 both. So loss is equal to 1 electron means gain is equal to 3 electrons. So 3 electrons gaining. Now let us make loss and gain equal. Therefore multiply this with 3, multiply this with 1. So take H3PO4 3 times, PH3 take 1 times. Okay, so phosphorus here 3, here 1, totally 4. So keep 4 here. Now we will balance oxygen. 4 3s are 12 oxygen, 3 4s are 12 oxygen balance. Hydrogen 4 3s are 12, here 3 3s are 9, here 1 3. So 12 hydrogens. Hydrogens also balanced. Okay, so H3PO3 undergoing disproportionation. Here phosphorus undergoing disproportionation means undergoing oxidation to highest oxidation number +5, and phosphorus undergoing reduction to least oxidation number -3. Then we will take H3PO2. H3PO2 hypophosphorus acid will take. Here phosphorus is +1, phosphorus +1 undergoing oxidation to give highest oxidation number +5. Then phosphorus undergoing reduction to least oxidation number, that is -3 in pH3. Like this it is converting. Now let us balance this one. Here +1 converting into +5 in the sense loss is equal to 4 electrons. +1 converting into -3 in the sense gain is equal to 4 electrons. Loss and gain equal. Therefore phosphorus is balanced. Oxygen you balance. Here 4 oxygen, but here 2. Therefore multiply with 2. Hydrogen 6. Here also 6. It is also balanced. It is also disproportionation. So in the phosphorus case, remember that this +3 phosphorus undergoing oxidation to highest oxidation number +5 in H3PO4, and undergoing reduction to least oxidation number -3 to pH3. Even H3PO2 also same. Phosphorus +1 undergoing oxidation to highest oxidation number +5, and undergoing reduction to least oxidation number -3. We are saying okay. This is about disproportionation we said. Sir, okay. Next we will see this fifth A group hydrides we will take. Fifth A group hydrides we are taking. Okay, fifth A group hydrides. In the fifth A group hydrides, in the sense what are the hydrides means NH3, then PH3, then ASH3, then SBH3, SBH3 and BiH3 hydrides we have taken. NH3 you know that ammonia. PH3 is called what in the sense phosphine we can say. PH3 is phosphine. ASH3 we can say arsine. SBH3 we can say stibine, and BiH3 we can say bismuthine. BiH3 we are saying, bismuthine we are saying. Okay, so hydrides we said like this. Now how the melting point and by melting point and other characters will be there for hydrides we'll see. Now we will take melting point, we'll see how the melting point will be there for hydrides we are taking. For ammonia, melting point is 195.2 Kelvin. 195.2 Kelvin we can say. Phosphine 139.5 Kelvin we are saying. Then arsine 156.7 Kelvin. Then stibine we are taking 185 Kelvin. 185 Kelvin. Okay, so how the melting point varies, that we will see. How the melting point is varying, that we are saying. Melting point depends on extent of close packing. Melting point depends on extent of close packing we can say, because melting point means solid into liquid only, no. Sorry, melting point depends on extent of close packing we can say. Now here if you see in this case how the melting point changes, you see that now melting point increases. Melting point increases if we go like this. Melting point is increasing if we go like this. So melting point increases. Why? Because extent of close packing increases we can say. And also we can say down the group size increases. Therefore van der Waals force of attraction increases. Therefore melting point increases we can say. From ammonia to phosphine, melting point what happens means decreases, because in phosphine intermolecular force is hydrogen bonding. In the phosphine, in the ammonia, intermolecular force of attraction is hydrogen bonding. In phosphine, no hydrogen bonding. In the phosphine, no hydrogen bonding. In the ammonia only hydrogen bond is there. In the rest of the category, hydrogen bond is not there. So for ammonia, melting point, what we have to say in the sense, melting point we have to say high when compared to phosphine. Okay, so melting point of ammonia is higher when compared to phosphine, we can say. Okay, so generally what happens to the melting point from phosphine to bismuthine, melting point what happens means increases, but ammonia to phosphine melting point decreases. Ammonia is having higher melting point because of hydrogen bonding. Okay, so melting point order like this is there. Okay, so among ammonia, phosphine, arsine, and stibine, which is having highest melting point in the sense, ammonia is having highest melting point, like this we can say. In that way, we let us go for let us go for explaining boiling point. Okay, so how the boiling point varies here, how the boiling point varies here, that we will see. So now we are discussing about boiling point. Now we will see NH